In our study of chemistry, we learned early on that there were two major driving forces of what caused a reaction to proceed in the forward direction. We said a long time ago that one of those driving forces was this idea known as metathesis, or the idea that when you have a change of state, when a substance goes, let's say, from an aqueous solution to a solid, right? In doing so, that will drive the reaction forward. The way you could kind of think of it is if there was an equilibrium that existed when everything was aqueous, as soon as a solid was produced, it left that equilibrium balance. And in leaving the equilibrium balance, what happens is that as you kind of remove this, right, the reaction in order to compensate makes more, and then makes more, and then makes more, et cetera, et cetera, et cetera. So this is why in a metathesis reaction, we could say that the reaction goes almost to completion, or 99.999% to completion, because the change of state is driving the reaction forward. But as we mentioned that way back when in the fourth unit of this whole year, one of the things we talked about was we said the bigger driving force in a chemical reaction is this idea of transference of electrons. Electrons being moved between one atom or one ion and another. So we referred to this transference of electrons as reduction oxidation, or redox for short. Now, one of the things that you have to recall, and this is important, is that when we look at the transference of electrons, how readily an atom loses electrons, how quote unquote badly another atom wants those electrons, that's going to help determine how easily a reaction happens. Now, we can take all of these terms that we've been talking about throughout the whole year, and what I'm now going to do is I'm going to come back to this idea of spontaneity. When we talk about one atom that readily gives up its electrons, in other words, maybe it's a large metal, it has a weak effective nuclear charge, or it has a very low attraction on those outermost valence electrons, right? When we talk about a big atom, we could say that that atom readily or spontaneously tends to lose the electrons, right? So through minimal effort, boop, the electrons fall off. If I now compare that to a teeny tiny atom, right? That teeny tiny atom whose electrons are close to its nucleus are going to probably have a strong attraction, or are more likely to quote unquote want those electrons. Say it a different way. A small atom tends to spontaneously gain electrons. So when a small atom, itty bitty, comes into contact with a big atom, ginormous, what we're going to tend to see is that the small atom will spontaneously, yoink, grab an electron, and the large atom will spontaneously lose that electron. Or a reduction oxidation reaction spontaneously occurs. Cool? So we spoke about spontaneity in the previous unit, and one of the conversations we had around spontaneity was this idea of will it or won't it? Okay, will it proceed in the forward direction or won't it go in the forward direction? Now, what we see then is that reduction oxidation is a good example of that actually occurring. And what's really important about electrochemistry is that it is through electrochemistry where we marry a couple of concepts together. We marry the idea of spontaneity, but we also marry the idea of electron transference. And if we have electrons being moved back and forth, then you and I call that electricity. So electrochemistry is going to be all about this idea of how quickly do electrons move, right? How easily do they move around, and how many electrons move around. Because the faster they're moving, the easier they're moving, and the greater the amount that are moving, all of that is going to give us not only electrical power, but it'll be able to give us things like voltages and amperages, which we'll speak more into later on. Now, electrochemistry, as we said, it's going to be all about this idea of measuring electrical current, right? And we'll speak more into what voltage and what amps are. But for now, what we want to talk about is that when we discuss electrochemistry, there's going to be two types of cells that we're going to be dealing with. Now, a cell is just a fancy way of saying a system in which you and I can easily track movement of electrons, right? So in a voltaic cell, this is where a spontaneous reduction oxidation reaction occurs. And you're very familiar with voltaic cells. You've used voltaic cells your whole life. Think of any battery. All batteries are spontaneous reduction oxidation reactions. How do I know this? Because if I put a battery into my little remote control car, sake of argument, the power supply or the electrical current is going to come from within the battery. So the battery is going to transfer electrons. As it moves electrons back and forth, those electrons are going to produce a voltage. That voltage is what allows my toy car to move, my radio control car to move. It's also the same thing that powers my cell phone. It's what's powering your laptop right now. All of those batteries are spontaneous reduction oxidation reactions. Now, let's just stop and think about a battery in general. Are batteries going to last forever? They don't. Well, why not? Well, the first thing I can think of is, in order for a reaction to occur, I need something that is going to be losing the electrons and something else that is going to be gaining the electrons. So if something is losing and something is gaining, right, then what happens if we run out of the substance that was losing? The answer is, then I won't produce any more electrons, or my battery will die. So from the simplest of places, not that this is the only reason, but one of the first things you can think of is that, well, if a battery is nothing more than a chemical reaction or a chemical process, let's talk limiting reactants. If you run out of one of them, boop, there goes your electrical current, right? Now, we're going to see later on that there's something else that usually happens before that, but for now, it's a good place to start. This idea of, like, you know, my amount of stuff in a battery is going to be significant. Second thing you want to think about when we discuss batteries is this idea of, are all batteries created equally? In other words, could I power your phone right now, sake of argument, with a couple of AA batteries or a car battery, right? And the answer is, well, I could, but would that really be that effective? Would it be efficient? Maybe after a couple of hours, my phone dies. I notice that my phone, I might have it on all day, and I can still watch videos and, you know, play a game and talk on the phone and text, right? Well, why can I do all of that with that particular battery? It's still relatively small. And maybe you look back and you realize, well, it's a lithium-ion battery, whatever that means. And maybe you've heard that, well, you know, you never want to mess around with like car batteries because they have battery acid in it. And you're like, well, what's the acid in there? And so one of the things that we're going to be looking at is that the type or the material you use to make a voltaic cell will determine how much voltage you get. It'll actually determine whether it's going to be a really powerful battery or a very weak battery. It'll determine if the battery is going to last for a long time or if it's going to be used up very quickly, right? But all of that is going to fall into this big, broad umbrella of a voltaic cell, and your takeaway is voltaic is spontaneous. Well, if we're talking about spontaneous, then there has to be the cousin. And so the cousin is the non-spontaneous reduction oxidation reaction, and we refer to those as electrolytic cells, right? So in an electrolytic cell, this is a process that does not happen on its own. You have to be driving the bus. You have to be supplying the energy, because if you don't, the reaction immediately stops. Right? Remember, a non-spontaneous process does not occur unless you give it extra energy. So when we think of an electrolytic cell, think of, like, you've probably heard of maybe like a gold-plated fork before, right? Or maybe you heard that, for example, your USB cables or excuse me, your HDMI cables, sometimes you'll see that the tips are gold plated so that it prevents oxidation, okay? Whatever. Anytime you've heard of a metal being plated onto another metal, as soon as you hear that, in your mind's eye, you're thinking, okay, that just didn't happen. So it's not like I took a bunch of gold atoms and they magically bonded to the metal. Anytime that you plate one metal onto another, that has undergone an electrolytic process, or it existed in an electrolytic cell where we drove the bus, we gave it energy, and as a result, the process then occurred. So, as you can see, when we talk about electrochemistry, at the heart of electrochemistry is going to be this idea of reduction, oxidation. And we spent a long time earlier this year going over reduction oxidation. So it is going to be mission critical if you've forgotten what an oxidizing agent is, what a reducing agent is, if you forgot about the standard reductions potential chart, or all of those things that revolved around this idea of oxidation numbers and electron transference. If you forgot any of that, then please go back to Unit 4, where we talk about types of reactions in solution, because most reduction oxidation, not all, but most, will occur in some type of solution. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.